welcome to Bulgaria.
Thank you. It's been a pleasure.
Thank you. This is your first time
This
in
is
Bulgaria.
my first time in Bulgaria. I was in Sofia and now in Varna. I've had a very enjoyable time. It's it's almost Mediterranean, but a little bit more European. And
Yes.
It's got a nice, interesting mix.
Thank you. So I want to ask you some things from your career and your research.
Sure.
So lately, what are the most exciting developments in genomic research that you see?
The most exciting developments in genomic research, I think there are two. I think we are getting to the stage now where we are going to be able to predict genetic diseases with reasonable probability that will identify patients that should be followed closely and intervened. I call that interception. That's on the translational side. On the science side, I think we're in the midst of the earliest stages of what will be a transformation, looking at biological processes as phase transitions and condensates, which will take us into the world of how cells undergo transitions by signaling with non-equilibrium effects, and will take us into dynamics. I mean, we basically do all our molecular and cell biology under stationary type equilibrium conditions, but a cell is not an equilibrium condition. So it isn't trivial to go to dynamics, but it'll take decades. But it is only in that perspective where we become more realistic about what we're able to say and not say.
And in that respect, a lot of people are wondering what are physicists doing with biologists, and so how do you feel the physics community being able to contribute to basic biology?
The physics community actually started molecular biology, and the most noteworthy person in that was Max Delbrück, who was a physicist of outstanding stature before he got interested in the gene, and he was the primary influence behind drawing Watson in a collaboration with Crick to discover the structure of DNA and the early formulation of the molecular biology community. We sort of drifted away, and we were so involved in gene cloning and all those sort of things that became somewhat routine, but terribly valuable. But now, as we've gotten more and more complex data, more and more technology that allows us to monitor and see within cells single molecules undergoing dynamic events, we are going to have physicists help us in both interpreting, projecting new concepts, and helping us with the technology. It's just essential. And I think the physicists are coming. They're gleefully getting involved, and we are gleefully embracing them. And one of the great things about this particular meeting that we're at here in Varna is, there is a dialogue between the physicists and the cell biologists and the chemists and the computationalists, and it's a very heterogeneous community. It's something I've called convergence. I've been looking for and projecting that it was a terribly important future in biology.
And indeed, the conference has been very, very fruitful and very useful. So you received the Nobel Prize for discovering introns, and also alternative splicing.
Mm-hmm.
So what are the latest developments based on your research at that time?
Well, I think the latest development is this whole emerging, and it's still only about 3 or 4 people in the world who believe this, this whole emerging issue, how phase transition and condensates are going to be a big part of the splicing process. And I basically came up against the wall 25 years ago. I could not penetrate that wall because there was no concept for what was going on, and now there is a concept, so I think it'll advance. But the interesting thing. Splicing was discovered 41 years ago. And we have the sequence of the human genome for now almost 15 years, 16 years. But we really didn't know the nature of the RNA expressed in a single cell until about 2 years ago. Well, the cell is the unit of biology. And that's where alternative splicing isoforms are very important. In the brain, every cell is almost different from every other cell. So we're just at the age in technology where we can look at this alternative splicing in tissue as heterogeneous as a brain. I have a ex-postdoc who's up in Toronto, Ben Ranko, and he's been championing really micro exons, and it's clear, and I don't know what it means, and I'm sure he doesn't know what it means, but it correlates with autism.
Yeah.
So, there's lots of indications that there's really very exciting things to learn out there from alternative splicing, and we're just at the moment where technology is going to bring us to being able to do it.
So how were you able to move from basic research and now, due to your research, you're attacking actually rare disease? So how did this translation? How was it enabled? How did it happen?
So my first experience with translation was back in 1978, right as recombinant DNA, DNA sequencing, DNA synthesis had all come together to allow you to do synthetic biology. And with Wally Gilbert at Harvard, myself, and a number of European scientists, we established Biogen.
Yes.
It was the third oldest biotech company, earliest biotech companies established. It's the oldest freestanding biotech company in the world. And our motivation was we had this fundamentally important new science. No one understood how it could be translated into the private sector. We had to hire postdocs and graduate students from labs who knew how to practice this, put together teams with clinicians and others, and there was just nobody. Big Pharma wasn't willing to take the risk. They just weren't willing to take the risk. So we organized a company, and then now it's something a little over 40 years ago. The company has got 8,000 employees. It's highly successful. The same thing happened in a different time, and that was in 2001, when the discovery of RNAi in 1998 by Andy Farr and Craig Mello. Every time I say Andy Farr's name, I follow it with he was a grad student of mine. So Andy and Craig discovered that they could put double-strand RNA in a worm, a little soil worm, and silence a gene. And we had no concept that there was a relationship between double-strand RNA and some activity in a cell that would silence a gene. So a group of scientists at MIT, Tom Tushel, Phil Zamore, David Bartel, worked out the biochemistry of that in about a year and a half. So then at the same time, it was discovered that small RNAs were just common of our cells, and they were regulating most of our genes. So we knew we had a biochemical pathway that would take small RNAs and silence a gene. And at the same time, just in 2003, the human genome was done. So now we had the sequence of all 23,000 human genes. We had a technology that literally from that sequence we could make a drug. And then the challenge was, could we deliver the RNA to the cell, in the cell, to silence a gene? And we established a company called Alnylam, raised the money, hard people, experienced biotech CEO, and now 16 years later we have our first approved treatment. And that's for a disease called transthyretin, a hereditary transthyretin amyloidosis. It's a mutant gene that makes a mutant protein that deposits in your neurons, and it will cause heart failure as well as nerve failure. And if the protein is produced in the liver, and we can deliver this RNA quite effectively to the liver, and therefore we can stop the progression of disease. In fact, patients improve when treated with this. And I gave a lecture up in Sofia on my way over here, and it was actually emotionally difficult because there were 20 patients in that room, and I could tell from how they walked into the room that they were at various stages of losing the ability to walk, or losing the ability to function. Some of them are college professors here in Bulgaria. One is came up to me within the time after the lecture. He came up to me and said hello. He had taken my picture, had it printed, brought me back cards that I could sign so he could give it to people, trying to get more support for transthyretin. And he's suffering from heart myopathy, heart failure due to this disease. So there happens to be a particular gene in the population of an area of Bulgaria that is quite, patients progress very rapidly if they have it. And to those patients, this is a miracle. There's nothing lacking. So it's really remarkably gratifying to see science, fundamental science, how to silence a gene in a worm, go all the way to a patient.
Amazing.
And it has happened again and again and again. Basic research, fundamental research, it takes 20 years, and you have to keep your eye on it to see the relationship, but it almost always brings you to a point where you can improve the lives of patients.
So you're also chair of the scientific board of the Stand Up to Cancer Foundation that is putting a lot of funding for translational research and basic research.
Yeah.
So how far do you think we're from curing some of the cancers like pancreatic cancer?
So I've been chair of the scientific advisory board of Stand Up to Cancer since it was formed. It was formed by a number of leading women in Hollywood, Sherry Lansing, Laura Siskin being two. Both were very successful heads of production laboratory facilities for movies, and a group who got together and say, we want to accelerate the rate of cancer progression in treatment of disease and control of disease. And we've had dream teams. The whole activity was established around the concept of collaboration across the country, across the world, of picking the leaders in a particular area, mixing clinicians with basic scientists, and having a dream team work for 4 or 5 years. In many cases, that's then supported by somebody else. We take pieces of it. It's been extraordinarily successful. We've had new treatments for pancreatic cancer. We've had new treatments for breast cancer. We had one of the biggest immuno-oncology programs in the country. Mm-hmm. We were spending more money, I think, in translating immuno-oncology than maybe NCI for a while. And that's changed how people are treated these days. When you talk about what's really happening in melanoma skin, 25 to 50% of patients can be treated with immuno-oncology. These are patients who would not have survived a year or 6 months, and they never see the disease.
Yeah, and this year, for the first time, they get Nobel Prize for cancer research.
This is the first Nobel Prize to Jim Allison. First Nobel Prize ever given for treatment of cancer. So it's 100 and
It's remarkable.
16 years and Nobel Prizes. This is the first one that had in its citation for treatment of cancer. We have CAR Ts that are designed to more specifically attack tumor cells. That's progressing, clearly working in leukemia. And we have a number of others. So we're turning cancer systematically into a chronic with some more cures. And for the patient, that's a big step forward. But you asked me about the most painful situation I know, and that's pancreatic cancer. My next door neighbor died of pancreatic cancer. The ex-president of MIT, who I was very close to, died of pancreatic cancer. My graduate student's mother died of pancreatic cancer. And they were all diagnosed within a month. One lasted 6 months, one lasted 2 years, one lasted 4 years. Pancreatic cancer, we really have extended their patient survival for diagnosed in a stage 2 or 3 disease, where 80% of them are. We've been able to extend their survival from 1 year to 2 years, or 2 years to 3 years, sometimes 4. But they never, very seldom, ever survive long term. We know if we can intercept that disease at stage 1 and 2, earlier in the disease process, and we use surgery and local radiation, we can actually cure half of it. So what we're working on in Stand Up to Cancer is to intercept the disease, and this is a integrated physicist, computationalist to biologist to clinician activity. We're taking genomic information and we're trying to collect it nationwide. Patients who have pancreatic cancer get their DNA sequenced. 10% of them have DNA damage, mutations in genes that are defective for repair of DNA. If you know that, then you know in that family you should screen very early. We're getting genomic information, we're looking at medical records. Turns out that many of these patients convert to being type 2 diabetes before they actually show the cancer. Pancreatitis is a large risk factor. So we want medical records for our patients. We can integrate genomic and medical records, and then we want imaging, because almost everybody in this country is imaged at one time in their career. So there's a redistribution of fat to muscle in patients as they develop this disease, many of them. And so we're trying to integrate all that information to identify patients earlier in the process, develop imaging methods that are transposable to every city in the country, and then to intervene in that cancer earlier. So I think that's a very important initiative, and we're trying to get more resources for it. And we're collecting European databases, Kaiser Permanente databases, any database we can use to try to get more information to bring to that process.
And I assume artificial intelligence is playing probably a big role.
Machine learning is critical in that, and actually natural language processing, because all these medical records, historically, the doctors don't use the same terms for every diagnosis, same degree. Some countries are very regimented because it's an integrated system. In this country, most countries aren't. So you got to be able to read the medical keywords, integrate what you're doing. You got to read your images are all going to be read now in the future by machine learning. We can even, I'm optimistic. I was having a fight with one of my colleagues here about machine learning. The argument about machine learning, it's all just correlative function. It doesn't tell you anything about mechanism. Well, I pointed out to him, every experiment I ever do is based on correlation. It's when I see correlations and then start thinking about mechanism, I make progress. So if I can integrate more and more data and see correlations, I'll make more and more deeper, faster progress. So the machine learning in the future will be mechanistic integrated with machine learning. That's what really good people are doing.
Lately, it has been very controversial due to the existence of new CRISPR-Cas technology, the production of or the made up of genetically modified embryos in China, and made the news all over the world. So, what is your opinion about modified humans?
Well, I think there are many ways of looking at that question. I think that importantly, but maybe not the most interesting, is where is the technology? Can we safely do it? And it's clear we don't know. One of the people who really took CRISPR and engineered the first mammalian cell is my friend. In fact, my graduate student's on that paper. But I declined to be on the paper because he was a young assistant professor. So I know a lot about the technology. We do not know the precision of the technology. We don't know the error rate. And, we don't know in many cases what, if you heal a gene, what that really means. So there's unknowns. And then there's the other side of this, and that is when you start designing people, you're imposing on them something that they have to live with the rest of their life, meaning they are designed, right? And that they will feel, people will view them as somewhat different. So who has the right to impose on someone else that issue? We have other ways of treating the disease genes. We're getting better and better. In the Mediterranean, beta thalassemia has basically disappeared. It's being by early embryo diagnosis. It's disappeared. So we have other ways of dealing with these issues. Artificial insemination or embryo transfer. So I just don't see any justification for doing it. And I certainly don't see any justification for doing it when you don't have the consensus of the community around you in doing it. So I just received a message today that there's a bill that's been introduced in the U.S. Congress to encourage the academies to work on producing an international set of guidelines that will deal with this issue, particularly deal with the issue of someone trying to do it in the back room and not getting the acknowledgement and input from other people.
And perhaps permits and support from the society.
Yeah.
So you grew up at a farm.
Yes, I did.
So do you have hobbies? What do you do when you don't do research?
I don't farm. The farm experience was important. It taught me how to work, because when it's a hot day and you have to put in the hay, you have to put in the hay, and you can't stop in the middle of it because it's hot. And the other thing it taught me, I didn't want to be a farmer. but my hobbies are cycling. I have a sailboat. I do a little sailing, day sailing sort of things. I like hiking. I have a little cabin up in Maine, and really very rural Maine. I used to fish more, but I don't fish as much now. I enjoy just getting outside and letting nature speak to me. That's part of what growing up on a farm means.
That's great.
Nature speaks to you when you live on a farm.
So for our young people, you don't play computer games.
I don't play computer games.
Thank you very much. It's been a pleasure to get
I got more important things to do in my life than play computer games.
Thank you very much.
Thank you.
It's been a pleasure.
Enjoy.